let's do it then. So this first problem says that a ball is dropped from rest and it falls towards the ground. The system is just the ball, okay? So what that means is gravity, or I mean, sorry, it means the Earth is not part of the system. And so what we want to do is we want to think about like what kind of energy it has up here and what kind of energy it has down there just before it hits the ground, okay? So that's really what we're thinking about. Now, it's dropped from rest. So what I like to do when I'm doing this is I always want to think about what's zero, you know, and first of all, I mean, we see U spring here, you know, there's no spring anywhere to be found. So that's definitely zero, right? So we can make that zero. And the way I like to show zero, as I said yesterday on these bar charts, is by just putting like a line, you know, at the zero mark. Now, for the initial, we see it's dropped from rest. So that means it's got no velocity. And as we discussed, when we have no velocity, there's no kinetic energy. Now, it's obviously dropped from some height. So it's got some UG because remember, gravitational potential energy is about height. The higher an object is, the more UG it has. So you can give it some amount of gravitational potential energy. But you can't. And here's the trick. Hold on, sure, I see your hand. Just give me a second. Because the Earth is not in the system, because it's not in the system, that means that UG, gravitational potential energy, is not part of the system, so it's not part of this L. So even that has to go away, and we just put a line there. Sure, was that maybe your question, or do you have a different question?
No, it's fine. That's what I was gonna ask because I saw
Oh,
you put it in, and I was like, wait, aren't we
nice.
supposed to?
Yeah, good job. So this is what the first L should look like, nothing in there, okay? Because it's just the ball. Now, let's do this just to mix things up a little bit. Instead of going across this way, let's go down. Let's look at this one. What about when we have the exact same situation, but now we do put the Earth in our system? Now we're going to have no kinetic, no U spring, but now we're going to have UG. Okay. So in some ways, it's easier or it's more meaningful to do this problem like kind of going downwards and kind of comparing and contrasting. Okay. So let's go look at our O's here now. And so, well, so obviously gravity is doing something to the ball and it's an outside force. And that's the key. Like gravity is now an outside, it's not part of the system. It's an outside force because it's not, the Earth isn't here. So that outside force does work. And that's what work is, when an outside force transfers energy. So we're going to do this. We'll put an arrow like that. We'll say work of force gravity. And since down below we transferred 3 units of energy, or we said UG had 3 units of energy, let's be consistent and let's transfer 3 units of energy in here. Okay. So let's think a little bit about what our final energy is going to look like. Well, the final is, let's see, it's right before it hits the ground. So it's basically, it is at a height of 0, right? So that means that our UG is 0 for both of these. U spring is definitely 0. Since the ball is in both systems, we can have kinetic energy. So basically all 3 units of energy are going to turn into or transfer or transform into kinetic energy. So we're going to have 3 units of kinetic energy in the end. All right. Any questions, guys?
I have a question.
Yeah.
Shouldn't it have like shouldn't the UG not be 0 because like it's still moving and like it's above the ground but like not on the ground? So
Sure. But the way we think about this is like this moment here, this final moment is like just before it hits the ground. So like if this is, if everyone can look in my little square, right? If my hand is the ground and this is the ball, like how high is it above the ground right now? It's not touching my hand, but it's basically 0 height, right? It's like 0.0000000001 meters above the ground. It's definitely fair to say, let's round that to 0. Is that good?
Thank you.
Good. Any other questions here? So one of the things I was talking to Surya about is how important these diagrams are. Like in the last unit, free body diagrams were important. And in this unit, these LOL diagrams are important. The reason they're so important is because they help us make our equations. So now we can easily make our equation, and our equation is 0 plus work of force gravity equals kinetic energy for the first example. And for the second example, we'd say UG plus 0, because there's no work, equals kinetic energy. And so then if we give you numbers, da 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 da, you can plug in your numbers to your equation that you just made and solve for whatever the unknown is. So what's the difference is? So mechanical energy. Now, we didn't really get to touch on that yesterday, but if you watch Miss Rona's video, she talked about it. And so mechanical energy is equal to UG plus U spring plus K. And so the difference is this. In example number 1, mechanical energy increased for the system because there was no mechanical energy to start with, and then there was mechanical energy. And that's because force gravity transferred energy into the system. In example 2, mechanical energy, sorry, where'd that go? Mechanical energy stayed the same. Mechanical energy stayed the same in example 2 because we had the same amount of UG as K afterwards. So the difference is, in example 1, mechanical energy increased, but in example 2, mechanical energy stayed the same, stayed constant. And that's just because of how we made our system. Any questions on that? The key is that mechanical energy is U spring, UG, and K. Let's take a look at this one. All right, so a child slides down a slide which has friction. Take the initial point to be point A. So he's not at the top. He's kind of somewhat down the slide. Right, so the child's partway down the slide and moving, right? That's important. And the final point is point B, where the child's at the bottom of the slide and moving, okay? The slide has friction. The system is the child and the earth, okay? So notice that in this case, what that means is that the force of friction is an outside force, okay? So force friction is going to do some work because it's not part of the system, the force of friction. So, all right, let's try and knock this out. So initially, again, there's no springs, so I'm just going to make U spring 0 for both of these. Initially, at point A, the child is moving, so he has some kinetic, and he's got some height, so he's got some UG. So I'm just going to make it up. I'm just going to give him like 2 and 2. So 2 units of kinetic and 2 units of UG. Now you could do anything. You could do like 3 and 1, 1 and 3, 1 and 4, 4 and 4, whatever, but I'm just going to do 2 and 2. Now we know that force friction is going to take energy out of the system. So the work of force friction is going to take some energy out. It's going to transfer some energy out. So I'm just going to do 1 unit of energy coming out. You could have done more than 1. I don't know. I'm just going to do 1. Then at point B, we see that the height of the kid is 0, right? They're at a height of 0. So we know there's no UG, which means, but he's moving, right? He's moving at the bottom of the slide. And we get to a bottom slide, you're moving. And so that means that we see 2 units of energy here and 2 units of energy here, but then 1 unit of energy gets subtracted off. So we see we've got like 3 total units of energy. So the kinetic must have 3 total units of energy. Any questions on that?
Shouldn't the kinetic energy be less than in the final than the beginning? Because like at a slide you stop at the bottom. I mean, on
Not
a
that,
slide you stop at the bottom.
not necessarily, The
Because like
reason you
he's still moving, but like shouldn't it be moving slower?
and it all depends on friction, right? Like, and so if there's a lot of friction, then you'll be moving slower at the bottom. But like you could imagine like a water slide where there's like no friction, then
Mm.
you're moving really fast at the bottom. So let's say that there had been a lot of friction, then maybe we do like 3 units of energy come out because of friction, and then there's only one left for kinetic. Does that make
Okay.
sense?
Hmm. Okay.
So, right. So like it all depends on friction.
Okay. Thank you.
Sure, good question. But regardless of how you do that, if you give this like 1 or 3, and if you give this 1 or 3, it doesn't matter. Regardless of how you do that, you're going to get the same equation down here. And that's, like I said, why the LOL is so important. Because what we get is we do K plus UG plus work of force friction. And we know when we get a value for that, we know it's going to be negative, right? Because the arrow points out of the circle. So we know that when we do calculate this, this is going to be a negative value. But let me go back to making my equation. We get K plus UG plus work of friction equals K. And so then again, like, right, and that's the beauty of the LOL is now we've made our equation. And now, if the problem gave us numbers, we can plug in numbers and solve. So again, let's think about our mechanical energy of the system. So we've got mechanical energy is K plus UG plus U spring. And so what we see is that there's less at the end. So there was more mechanical energy at the beginning than at the end. So what I would say about that is uh, because because the work of friction removes energy from the system, there's less mechanical energy at the end. So less mechanical energy at the end because work of force friction removes energy. Okay. Any questions on that? So let's take a look at the last couple here if we can. So a box is held at rest attached to a compressed spring. Okay, so we're gonna have some U spring now. The spring launches the box horizontally and the box slides to a stop on a rough surface. Okay. Um, so right, okay. So after being released from the spring, okay. So let's see. This is interesting. So the spring, okay. So our system now, interestingly enough, it has the surface in it. So force friction is in the system. Okay. It's not outside the system, it's in the system because the surface is in the system. So what is this going to look like? Well, first of all, I think we need to make sure we understand when is each thing. So we'll say initial energy is right there. And we're going to say that final energy is when it's stopped. Okay, just to be clear, final energy is when it's stopped. All right, here we go. So first of all, it's not moving to start with. So it's got no kinetic energy. It's got no height. So it's got no UG. So it only has spring potential energy. How much? Let's say 3 units. You could say 1, 2, 3, 4, whatever you want. Now, since force friction's in the system because the surface is in the system, there's no work. So we would not say work of force friction. We're not going to do that because friction is in the system. Okay, so that's not going to happen. But what we do need is this. So if we look at the end, it's stopped. So it's got no kinetic energy. It's got no height, right? It's still on the ground. So it's got no UG. And the spring is now at its natural length. So there's no U spring. So for a moment, you should ask yourself, this seems impossible, right? We've got 3 units of energy here, no work, and no energy here. That's impossible. We need all our energy accounted for. And so what we're missing, and if you watched the video that I sent out yesterday, is we're missing E thermal. There's thermal energy. okay? Because that's what happens when the block rubs along the ground. That friction heats up the block and the ground, and so there's thermal energy. So there's 3 units of that. Any questions? So if we had numbers, we can plug in our numbers because we've made our equation. U spring plus 0 equals E therm.